we're going to look at adding and subtracting fractions now, and a couple of models that help us grasp what's going on with those. When we were adding whole numbers, we thought of just combining two sets of numbers together, or subtracting. So we would do the subtraction, we would model it, and then take away so many. So with whole numbers, we can have that kind of model of combining or subtracting. So we can also do that with fractions. So adding two fractions is just another way of combining two amounts. They're just parts of a whole instead of whole numbers. So this model is with fraction bars. So if we have the same denominator, we can easily add these, but let's look at what we have here. Okay, so in this bar, we have 4 of 6 parts total shaded. And in this bar, we have 3 of 6 parts shaded. And if we put them together, okay, so we put this where this one stops, and then we add up how many parts are shaded, we have 1, 2, 3, 4, 5, 6, 7, and these are each sixths. A common mistake would be to say that you could have, this would be 7/12ths. But these pieces are not twelfths of a bar. The pieces are only a sixth of the entire bar. Now, if I place these side by side, I can see that these two fill up the rest of this bar, and then I've got a sixth left over. So we can say that either this is 7/6 or it's a whole 1 1/6. When you have unlike denominators, however, you don't have the same kind of parts you're adding. You can think of this like, you go and you have so many euros and you have so many dollars and you have so many Japanese yen, right? But until you know how to convert them to the same currency, then you really don't know how much you have. Okay, so in the same way, if I try to add 2/5, so 2 of the 5 parts of that purple bar shaded, with 1/3, I don't have the same kind of parts that I'm adding. Now I can get an idea maybe of about what this should be, but I want to know what it is exactly. So we're going to do kind of a form of conversion. Okay, so we're going to replace these fractions with fractions that have the same denominator. So we learned when we found least common multiples that we can take different lengths and put them together so we can find the least common multiple between two numbers. Well, for 5 and 3, that least common multiple is 15. So what I want to do is divide each of these bars, the purple and the yellow, into 15 pieces. So if I take the purple bar and divide every small piece into 3 pieces, then I'm going to have 15 pieces altogether. And if I take the 1/3 bar and divide each of these 3 into 5 pieces, that each of the smaller pieces, there are 15 of those in the yellow bar. So now I have the purple divided into 15ths, and what I have shaded is 1, 2, 3, 4, 5, 6 of the 15 are shaded. And then in this thirds bar, I have 1, 2, 3, 4, 5 of the 15ths shaded. Now I have two fractions with common denominator. So how many pieces do I have shaded? 11. What kind of pieces are they? 15ths. So 2/5 and 1/3 is the same as 11/15. Not because I did some sort of magic, but because I made each of these into 15ths so that I can add them. So if you want to find a common denominator, not necessarily the least common one, you can always multiply the denominators together and get something that's a common multiple. Okay? And then, once you have a common denominator, you add the numerators and keep the same denominator. Okay, so when we add fractions, it looks like this. So if I want to take BD, now this may not give me the least common multiple. If they're relatively prime, it will. But I can find a common multiple by multiplying B and D. But we first have to agree on the fact that if I take a fraction and multiply it by 1, or let me say A over B here, and multiply it by 1, am I changing its value? Does that still equal A over B? Yeah. Okay. Well, what is D over D equal to? It's equal to 1. So if I take A over B times D over D, I get AD over BD. Okay. Sorry, AD over BD. And that's where I get this first number. And here when I take C over D and multiply the top and the bottom by B, I get that. And then I just add the numerators and keep the same denominator. Now this won't, if B and D are not relatively prime, they don't have any factors other than 1 in common, then you'll get a fraction at the end that may have to be reduced. And always reduce your fractions to lowest terms. Okay, now your book, and this is taken from the exercise set in your book, uses this area model. And an area model is also another way to do this. Okay, so here, what's shaded? I have 3/4 plus 1/3 of this is shaded. So what I'm going to do is I'm going to divide each of these bars into thirds, and then I'm going to divide each of these bars into fourths. And it's not real pretty, but you get the idea. So now, instead of saying that this is 3/4, I can also say it's 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12 is shaded. Okay, and I can say now I have 12 parts, but I only have 1, 2, 3, 4 of these parts shaded. Whoops. My stylus went a little crazy here. So then we add the numerators. And we get 13 out of 12. Now, if I put 3 of these and covered that up, I'd have a whole and 1/12 left over. So if I took 3 of these and filled in the empty parts right here, I would have a whole filled and then 1/12 left over. So we've been looking at mixed numbers and proper fractions, where the numerator is smaller than the denominator, and improper fractions, where the numerator is bigger than the denominator. Okay. Now, so if you're going to add mixed numbers, you can add the whole numbers and then add the fractions separately and then combine your answers. Okay. The same thing happens though if the denominators are unequal, then you're going to have to make sure you find the common denominator first. Now, example D actually isn't included here. It's from the other book. But the same thing holds. Whether the numerator is bigger than the denominator or not, you have to get a common denominator. Okay, now subtraction is the same for fractions as it is for whole numbers. Okay, so we can think of it as take away, comparison, or missing addend. Those all apply to fractions. Okay, so here I have, I'm going to think of these as a comparison concept. I want to find out the difference. So I want to find out between 1/2 and 1/6, how much has to be added to the 1/6 to get the same amount we have here. Well, I can tell from here that if I were to divide these up, so they both have 6 pieces, then I have the same as 3/6 shaded here minus 1/6 shaded here. So what I have to do is I have to add 2/6, which reduces to 1/3. Okay, so here we have 5/6 minus 1/4. Okay, now we can kind of estimate this, okay, because here I have 1, 2, 3/6. Okay, here I have the amount that's different. Okay, so I can kind of estimate this to be somewhere between 3 and 4/6. I really don't know exactly. So this in here is somewhere between 3/6 and 4/6, but I can't tell exactly, but I want to know exactly. So what I want to do is divide them up into the... Okay, so I know that the least common denominator, the least common multiple of 6 and 4 is 12. So I'm going to take these 6 and divide each piece in 2 so that I have 12 pieces. And that's what you see over here. The same amount is shaded, but these pieces in 12s are 10 of the 12s are shaded. Okay, I want to get the fourths to have a denominator of 12, and I have to multiply 4 by 3, so I am going to divide each of these into thirds, a third of each, 3 pieces. So then, when I look at the shaded amount, I don't have to call it 1/4, I can call it 3/12. Now I have the same subtraction problem, just written with different denominators. This I subtract just like I would add by subtracting the numerators to get 7 and keeping the same denominator. Or how many pieces are different between 10/12 and 3/12, if I'm kind of thinking of a comparison method. Well, 7 of those 12s are different. Okay, so the difference between these two fractions is 7/12. Now, here's an area model, but it's much like what we're doing, except we have a 1/3 shaded here. And here we have 1, 2, 3, 4, 5, 6 shaded. Okay, so I need to make sure they have both the same kind of parts. And the LCM of 3 and 6 is 6. So I need both figures divided into 6 pieces. So this one's already in 6 pieces, and these are in thirds, so I'm going to divide each of these in half, and now I have sixths. So what's shaded here I could write as 2/6. Now I want to take away one of those sixths, and what do I have left over? Just a 6. So I can think of it like take away. And the part that's remaining shaded is 1/6. Okay, so we have a general rule for subtracting fractions, because you don't have to get the least common denominator, just get a common denominator. Just makes your work easier if you get the least common denominator. So it looks just like our multiplication rule. Okay, so I'm going to multiply here by d and d over d, which is 1. Multiply here by b over b. So now they both have bd in the bottom. AD minus BC, and they keep the same denominator. You also need to keep in mind that if you have mixed numbers, so if you have 1 and 2/3, excuse me, 1 and 2/3, and you want to subtract off 4/3, you have to get a common denominator, which we have one here. So let's change this to a mixed number, or to an improper fraction. 3 times 1 is 3, plus 2 is 5/3, minus 4/3, and we know that 5 minus 4 is 1 over 3. Suppose I have 1 and 2/3, and I want to subtract 5/6. I'm going to go ahead and write this as an improper fraction. So that's 5/3 minus 5/6, but I have to have a common denominator. The common denominator is 6. So to get a 6 over here, I multiply the top and the bottom by 2. So this problem becomes 10 over 6 minus 5 over 6, which gives me 5 over 6.